Hey everybody, my name is Scott, and today we're going to solve the peak index in a mountain array problem on LeetCode. Let's take a look at the problem description. We call an array a mountain if the following properties hold. Its length is greater than 3, and there's some index I such that we have a of 0, a of 1, up through a of I, all being less than each other, an increasing sequence, and then after I, a decreasing sequence, where a of I is greater than I, a of I plus 1, which is greater than a of I plus 2, all the way down through a of a dot length minus 1, the last element. We're given an array that is a mountain, and we have to find the index of the top of the mountain, basically. Here's an example, 0, 1, 0, return the index of 1, because that's where the top of the mountain is. You see, this index right here at 1 is obviously greater than everything to the left of it, and everything to the right of it is less than it as well. And then here, 0, 2, 1, 0, top of the mountain here at 2, 2 being greater than everything to the left and the right of it. So, the key observation to this whole problem is this strict property here. A of 0 is strictly less than a of 1, strictly less than a of 2, which is all the way up through strictly less than a of I, the index we want to find. And then to the right of that, it's a greater than relationship. So essentially the way to look at it is we have an increasing sequence up till we get to the index that we're looking for, and then a decreasing sequence down till the end of the array. It's not a peak finding problem like you may have heard of in other fields of artificial intelligence, where you'll have different slopes through your search space and you have to go finding them. This is different, and when I first read the problem, I didn't read the properties that well, the problem definition, to where I didn't quite see the solution straight away. But once you take note of this fact that everything to the left of this index we're looking for is an increasing sequence, and then everything to the right of it is a decreasing sequence, it makes the problem much easier. Now there's two ways to do this. The first simple way of doing it is just a linear loop through the array, okay? You'd start your loop down here at the bottom of the array, and you'd loop forward looking at each element, and then eventually you would find an element where it stops increasing and it starts decreasing, and that would be the index you would return. And the time complexity would be big O of n. But we're not going to do that. We're going to use binary search. And if you don't know what binary search is, the idea is when we're using binary search, with every decision we make, we get to discard half of our search space. Okay, so when we start our binary search algorithm, the entire array will be our search space. We won't know where the answer is. It can be anywhere in the array. But at every decision we make, every time we loop through, we are going to throw away half of the search space. We will be able to eliminate it and say, okay, the answer is not in this half of the array. And then we only have to continue on with half of the array. And then the next decision we make with that half of the array, we will again say, okay, there's this half of the remaining array that the answer cannot be in, and we will go continue our search in the other half, and it continuously slices your search space just like that. And the time complexity of an algorithm that uses binary search in that way is log of n, okay, which is much, much faster than linear. Linear is fine for obviously a lot of things, but when you can find a log of n solution, it will be much quicker. So here's how we're going to do it. We're going to have a low pointer, which starts pointing at the beginning of the array, and a high pointer, which is going to point at the last element. Basically, these pointers, they are delimiters of what our search space is. And at the beginning, the search space is the entire array. And we will loop while our low pointer is less than our high pointer. Basically, the reason you loop while your low pointer is less than your high pointer is that is basically a way of saying, okay, we still have search space to search through, okay? If they're the same, then you've narrowed it down to one element, and you've found the element you're looking for. The first thing we want to do is calculate the midpoint of these two elements. So at this point, what we've set up is we have a pointer at the left side of our search space. We have a pointer at the right side of our search space, basically a pointer at the beginning and the end. And we've calculated the middle. We have a pointer now at the middle of those 2 points. So there's 3 pointers set up now. If the element at the middle point, which we just calculated, is less than the element at the midpoint plus 1, what must this mean? Well, think about it for a second. We've just determined, we've looked, okay, here's the midpoint of our search space. Is it less than the element that comes after it? Let's look back at the properties we're given. Let's say we calculate the midpoint here, right? And it's less than the number to the right of it. By looking at this property, what that must mean is that we're still on the increasing slope. We're going up. We're going up to the peak. So we're somewhere over here. So what that must mean is that the peak, which we're looking for, cannot be in the left side of our search space. Okay, so we can discard all of the elements to the left because we know we're still increasing and that the peak cannot be to the left anymore. So what we'll do is we'll take our low pointer and we'll set it equal to the middle plus 1. And the reason for the plus 1 is we can also discard the mid, because obviously the element at the middle cannot be the peak because it's less than the element to the right of it. Else, okay, so the middle element is greater than the number 2 to the right of it, which must mean it is either the peak or the peak is yet to come to the right, okay? So what that means is we can take our high pointer and set it equal to the mid. And that chops our search space in half as well. And then all we'll have to do down here at the bottom is return the low pointer, which will be pointing at the peak when this loop is done. Okay? So let's just, first off, let's make sure that this works before we go into explaining something. I'll make sure it actually works. Alright, accepted solution, cool. So this is the idea with binary search. You set up a pointer at the beginning and end of your search space, you find the middle of the search space, and then each decision you make casts away half of your search space. And look at the decision we're making here. We say, we find the middle element, and what happens if the middle is less than the number to the right of it? Then we know that the peak must lie to the right of our search space, after the midpoint, okay? If it's not, then that means that we have either found the peak, or the peak lies to the left of the search space. So each decision we make, we're able to discard half of the search space. And this results in an algorithm of time complexity, log of n, which is very fast. So that's the idea here. Whenever you see something where you're searching through an array and it's got some sort of restriction on how the elements are ordered, binary search is always a good idea. For instance, here we had this setup, this restriction here on how our elements were ordered. Okay, they increase, they hit a peak, and then they decrease. And when you have an order like that, it makes binary search very good because you can find some sort of a relationship where at each decision you make, you throw away half of your search space. Another way that binary search comes up a lot is if you need to search an array for something, and the time complexity is going to be really bad to search that array. what a lot of times you end up doing is sorting that array first. Now, sorting, the fastest you can sort is n log n, right? But let's say that you need to search through an array twice to do something. Well, that's n squared, okay? But if you first sort that array in n log n time, and then you have some binary search algorithm you can use, then that's just log of n, then your total time complexity just ends up on n log of n, the time that it takes you to search it, instead of doing multiple passes through an array, n squared, n cubed, whatever it ends up being. So that's how binary search is helpful. Again, you're searching an array that has some sort of ordering on its elements. A lot of time, binary search will help you out. And that is it for this one.